right? Because this is negative charge, so both of them, rest of them are positive. So due to this plus q charge, force would be attractive. So the force would be in this direction due to q. Due to this plus 4q, this is also, this B point is also attracting this minus q charge. So this would be in this direction. So they are balancing each other, right? One is left, the other one is right. What about this point? At this point, this thing we discard, right? So now we are taking the contribution from this one and this one. So if I take this plus q charge, right? So the force would be attractive. So this is right hand side. And due to this plus 4q charge, both are positive. So force would be repulsive. So this is F4q, right? Similarly, if I talk about this point, so at this point, this q is attractive and this plus small q is repulsive. So you see that all these points are balanced, right? This was not the case for plus q charge. If I had plus q charge, so then I had one directional force. But for minus q charge, every point is balanced, right? Is it clear? Yes, is it clear?
Yes, sir, it's clear.
Okay, so then I have to take the negative charge, right? So that is why the nature of this charge would be negative, whatever the charge I am putting between these two charges. If the whole system is at equilibrium, then the charge should be negative. So I have three conditions at point A. At point A, F4Q, this is equal to FQ, right? At point B, at point B, FQ is equal to FQ. And at point C, right, FQ is equal to F4. So these are the conditions that I will have. If I solve these conditions, I have to apply the Coulomb's law. Then I will get the values of the charges. So then I can calculate what is this distance, which is x, right? This would be, let's say the total distance is L from here to here. The distance is L, so this would be L minus L. And then I can calculate everything, right? I know what is Coulomb's law. I put all these values and then I can solve. This is the idea of system static. Quickly note this thing down and then we'll do a couple of questions. Quickly note this thing down. And whenever you have noted, just tell. Yeah, whenever you have noted, just tell.
Finish, sir.
Finished. So let us do some questions based on Coulomb's law, and then these will be pretty much. Let's do some questions.
Okay.
Okay, so let's take this question. All these questions are based on Coulomb's. Right, so the acceleration of an electron due to the mutual attraction between the electron and proton when they are 1.6 angstrom apart is right. So we have to find out what is the acceleration of the electron, right? So we know that what is the force between right? What is the force between the electron and proton, right? We know that that would be due to because these are two charges, right? And the charges are plus E and minus E. So then Q1 is E and Q2 is minus E. We are only considering the magnitude, so then we will just take the positive E. So the force between these two things would be how much? That would be K Q1 Q2 by R square. The separation is given, right? And we want to find out the acceleration. We know that this force is related with acceleration as ma, right? And this is q1 q2 by r square. And we also know that this acceleration, we are calculating the acceleration of what? Electron, right? So we have to take the mass of the electron. So this is mass of an electron and acceleration and then k q1 q2 by r square. So acceleration is simply k e and e divided by r square and multiplied with mass of it. All these values are given. K is how much? 9 into. Yes, your internet is fluctuating, right? So,
Yeah, yeah.
okay, so what we were calculating. So K value is given 9 into 10 to the power 9, right? And E we know what is the 1.6 into 10 to the power minus 19. And this is square, so 1.6 into 10 to the power minus 19. And then we have angstrom, right? 1.6. Okay, and this is squares. 1.6 into 1.6. How much is angstrom? How much is angstrom? One angstrom is how much? These units we have to remember, right? So let's say we have 1 nanometer. Nanometer is 10 to the power minus 9 meters. Angstrom is 10 to
10
the
raised to 10.
yes, minus. Yes, correct. So this is angstrom, right? Put this value because this was a square. And then we have this mass of 9 into 10 to the power minus 50. Okay. And we see that all these values are cancelled, right? So 9 is cancelling, 1.6 cancelling, 1.6 cancelling. So now all these answers are in the powers of 10. So let's calculate that. This is 9. This is minus 19. So that is minus 10, right? So I can cancel this thing, and 1 minus 10. Now what do I have? So this is 10 to the power minus 19, and this is 41. So this would be 10 to the power 41 minus 90. So how much is this? It's 10 to the power 22, right? So the option would be C. If everything is, so this would be the answer, right? This is meter per second square. Is it clear? This was a very simple question, right? just using the idea of
Yes, sir.
Coulomb. So quickly note this thing down and then into the next question. Yeah, whenever you have noted this thing.
Done, sir.
Okay, so let us try the next question. Right. The, okay, this one we have done in the yesterday's class, right? So let's do this.
Yes.
The percentage one we have done, so we can mark that. Because this question we have done in the yesterday's class, right? This is complicated question, right? Slightly a complicated question. Let's do this question, right? What do we have? And before we do this complicated question, we should do a simple one, right? But yeah, so okay, let's do this. So we have two identical charge spheres suspended from a common point by two massless string of length L are initially at a distance d. So we have this right, and two massless things are separated by a distance, right? And the length of the string is L. So both of these are L, and the separation between them is right. Both have identical charge, so both have Q charge and Q charge, right? And they are at equilibrium, right? So they are at equilibrium, and let's say the angle between them is this is the angle between, and because these are equal angles, so this separation would be by 2 and t by 2, right? Now the charge is depleting, right? So the charge begins to leak from both the sphere at a constant rate. As a result, the sphere approach each other with a velocity v. Then v varies as function of the distance x between the sphere as what? So the now charge is leaking, right? The charge has become how much? So let's say that the charge has become, let's say this is q dash, and then this is q dash, and let's say this distance is, so this is x distance, and this is x distance, right? This is L, and this is L. So the charge is depleted, right? So let's solve this equilibrium condition first, and then let's see that what is happening, right? So this is the ideal case. Now let's say that and the angle remains the same, right? So we have fixed this angle. The charge begin to leak from both the sphere at a constant rate, as a result, the sphere approach each other with a velocity. Then v varies as a function of distance x. Oh, the distance x between the spheres. This whole distance is x, right? This whole distance is x. This would be x by 2, and this is x by 2, right? So now let us calculate the equilibrium condition. Right, let's calculate the condition. So what would be that? So we know that this is tan theta, and this is how much from here. So this is these are the two charges, right? This is the string. So how many forces are acting on these two charges? How many forces are acting on these two charges? Yes. So this is the charge. This point, if I want to draw the free body diagram, so we have just done the previous chapter, right? Or the, the last two chapters. So in the earlier two chapters, we were talking about the free body diagram. So I have to write the equilibrium condition for this chart. So I have to count how many forces are acting on this chart, right? That is what I have to count. So how many forces are acting on this charge? Can you tell me? Yes. Let's say the mass of this charge is m. So this has m mass. This has also m. So can you tell me how many forces are acting on this thing? Yes. How many forces are acting on this thing? Okay. So yeah. So let's write all the forces, right? So first thing we are doing this electric charges and field. These are two charges. So first would be the electrostatic force, Coulomb force, right? So if I want to calculate the Coulomb force at this point, what would be the direction of Coulomb force? Left, right, or left? What would be the direction? Yes, what would be the direction of Coulomb force? Yes, Nabil, what would be the direction of Coulomb force? Yes. Okay, so let me just because these are positive charges, right? Force would be repulsive. So this will repel this
The answer is option D, right?
option D. You have calculated the answer already.
Yeah, I was doing that.
Oh, you were doing the calculation.
Yeah, yeah.
Okay, but oh, so if you have done the calculation, so yes, x to the power half is the right answer, right? So yes, Let me check that if it is the right answer. So, okay, so I have, did I do this? No, I have not marked this one, but okay, this will go in here. So right, so this is x cube. So 2 dq by dt, and then this is yeah. So I guess that would be the answer. So this is 3. So that would be 3x squared, but okay. So x by uh, okay, I have to see. I have to calculate and then I can say whether it is. So if you have calculated already, right? So any doubt in this problem, if you have done this problem already, any
No, sir.
doubt in
No,
this?
sir.
No. Okay, so let's do the next question, right? But this is
Okay.
important, right? So we have to just calculate the free body diagram. So how did you calculate? You have taken these two cases, right? Case 1 and case 2. And we have to write, we have to mark all the forces, right? So one is this Coulomb force. And then what were the other forces that you have written? What were those other forces? Yes.
Moments are taken.
How many forces are acting? We have to write the free body diagram. Yes, you got disconnected. Hmm. Yes, Nabil, can you hear? Oh, you had problems, network issues. Oh, the router failed. Okay, yeah, don't worry about that. So I was talking about the courses, right? So how many courses are there, right? That we have to, yeah. So we have to talk about how many forces are acting on this thing. So this is the scenario, right? So this is the scenario. There are Coulomb force, and then there are this tension, and then there is this mg weight, and there is this gravitational force also. So there were actually four forces that we have to take into account. So this is mass m, right? So due to these masses, there would be this gravitational force also. But we will neglect this thing because the Coulomb force, so this Coulomb force is very, very larger than this gravitational force. So we will neglect whenever we have charges, then we neglect the gravitation because that is a very small part. So that part we can neglect. So then what we can write? So if we talk about this case, right? Because this was the previous case, now this is the case, and we have to find out x, how this velocity is changing. So let's try to find that out. So this is the Coulomb force. This is mg, right? This is theta, and this is tension, right? So this is your tension. This is the tension. What is this is the tension. So this will have because this is angle theta. So this is theta angle. So this would be t sine theta, and this would be t cos theta. So t cos theta is t cos theta is mg, and t sine theta, that is Coulomb force, right? So if I divide this thing with this thing, so I will get tan theta as Fc by mg. So Fc is simply mg tan theta, right? And I know that what would be this Fc. So charges are q prime, right? Charges are q prime. So that would be simply k q prime square divided by this whatever. The separation between them is x square. And then mg, and because this theta is small, or I can write this theta as what? So tan theta is how much? This is theta, so p by p. P is how much? This is L, and this is x by 2. So this is hypotenuse minus this is perpendicular. So hypotenuse square minus perpendicular square, right? Because this thing is very small, so this I can neglect. So this would be tan theta would be simply x by 12, right? If I put this value in here, so this is x by 12. So this thing is how much? Prime square, and this is mg by k, and x cube by 12. So how much is this thing? This is mg by 2kl, and I can write it as constant and then x cube. So this is q prime square, right? So how much is q prime square? that is Cx cube. Now what would be q prime? That is Cx, and this is power 3 by 2, so I can write it as 3 by 2, and this is also 3 by 2. Again, this is a constant. So q prime is behaving, or q prime is varying as x3 by 2. Now the rate at which this is decreasing, if I take the rate, so this is dq prime by dt, this would be how much? That would be 3 by 2 and x3 by 2 minus 1 into dx by dt. So how much would be this thing? I know that this is a constant. So they have said that the charge is decreasing with constant rate, right? So this is a constant again. I name it as k, and this is 3 by 2, and x 3 by 2 minus 1. So this is x half, and this is v. So now I take this x power half in the left hand side. So v would be proportional to x minus. So that is the answer, right? We have got x plus half, but the answer would be this. Okay, is it clear? So this is the correct answer. Yeah, please correct that. Where did you make the mistake? Yes, is this part clear? Right? Yeah, so the answer would be this minus half. So v would be x minus half. So we have to just apply this idea of equilibrium, right? All these forces are equilibrium, so we have these two conditions, and we apply this thing, then we'll get this answer. So this was this question. Now you just correct whatever portion was incorrect, and then we'll move on to the next part, right? We have to quickly solve some of the questions. Just quickly note this thing. Just correct the mistake, and then that move on to the next part. Whenever you have corrected those portions, just yes. Whenever you have corrected that, you have noted just noted. Good. Now let us try some other question, right? We have a similar question, but that one is Delhi, right? This one is Delhi, right? So we have two positive ions, each carrying a charge q, are separated by a distance d. If F is the force of repulsion between the ions, the number of electrons missing from each ion will be one. Right. So again, this is a very simple question based on Coulomb's law, and we have to find out what is the number of electrons missing from each ion. Right. So the charge on each positive ion would be due to the number of electrons which are missed. So the total charge that would be simply n. Right. And the force between these ions, right? So let's say this is one ion and this is another ion. Both are positive. And the distance between them is how much? Distance is d. So the Coulomb force between them would be how much? That would be simply kq square, right? Divided by d square. So this is the Coulomb force. And we know that this F is there and K and Q is how much? That is NE. So whole square divided by D square. So how much would be this thing? So this is FD square by K and this is N square and E square. So N square is how much? This is what we want to find out. This is FD square divided by K and then E square. So n would be simply root of fd square divided by k and e square. So this is the answer, right? But they have written in 4 pi epsilon naught, so we write this k as 1 by 4 pi epsilon naught. So this becomes 4 pi epsilon naught f e square by e square. So that is the answer, right? This was the simple question, right? What is the correct option? So this one is the third. Right. Yes. Okay. So if it is clear, then quickly note this one down, and then we will see. So let me see if I have some other questions which are important. So that is the idea that applies to the Coulomb's law, and then equilibrium condition, and then you have all those like tensions and buoyancy is also there, but that is not that part. Yeah, whenever you have noted this thing down, yes, whenever you have down, down to see if we have other question. Okay. An electron is moving around the nucleus of hydrogen atom in a circular orbit and Coulomb force between. Yeah, this one is very simple. So yeah, this is. So these are all about Coulomb's law. Now let us understand. Right. Let us understand what is the other topic, which is electric. So in electric field, what have we done? Right. Electric field is force per unit charge, and it has the same direction as the Coulomb force, right? And it has symmetric properties. So if we have a geometry which is symmetrical, then at the geometrical center, if all the charges are identical, right? If all these charges are identical, then the force or the electric field at the center, that would be zero, because the electric field they follow the superposition principle. That thing you have done already, right? So electric field follows superposition principle, and from geometry, if we calculate the electric field at the geometrical center, but the charges should be equal, right? If there are different charges, then the answer would be different. But if the charges are equal, then at geometrical center, the electric field is right. And whatever the point at which the electric field is zero is called the neutral point. So that thing is there. And for a point charge, right? For a point charge, what is the electric field? So we have to remember a few things. So for point charge, we use that. Have to remember these few points. So for point charge, electric field, the magnitude is simply kq by r square, right? And for infinite charges or for finite charges, right? For finite charges, the electric field is sum of or superposition principle, right? And then you have also learned that what is the electric field for dipole. For dipole, you have 2 points, right? So for dipole, you have electric field axial, you have electric field equatorial, right? E axial is how much? How much is E axial? Do you remember that? So you have to remember that this is 2 kb by r, and E equatorial is minus kb by r. Both varies. So electric field varies as 1 over r cube for both the cases, right? For dipole, both the electric field varies as 1 by r cube. And what is axial point? What is equatorial point? So if we have this dipole, right, this would be the, because the, let's say the distance is 2a, right? The separation between them is 2a. And this line is called the axial point. So this is E axial. And let's say this is the distance r. And the equatorial point is this one, perpendicular one. So this point is E equatorial, right? So at E axial point, the electric field is in the direction of the dipole moment. What is the dipole moment? Dipole moment is 2 into, or this is simply the charge into separation. So whatever the charge into separation, that is 2a. And the direction is p at, right? This is the dipole. So these are the things that we have to remember, right, for electric. And then when we will learn the Gauss law, so then we have electric field due to a hollow sphere, that part is stuff. So these are the things that we have to remember, right? Electric field to all these things. Is it clear? Is it clear? Okay. Yeah, so you have to remember all these things, right? And what are the other things that we have to talk about? Yeah, so okay, there is this line charge as well, right? So for line charge, you don't have to remember the finite line charge. You have to remember only the infinite line charge, and that part we'll study in Basel, right? So all these things are this. Okay, good. So yeah, now we have understood the idea of this electric field due to different systems. Now we'll do certain questions, right? So let's do some questions. And there is also this. So I will talk about this thing already. So there is also this thing which is called the. Whenever I change this thing, so this. So this is called force on charge particle in external electric field, right? So this is force on charge particle in external electric field. So let's say we have this electric field. This is electric field, and I put some charge in here. Let's say plus Q charge, right? So this charge will experience a force due to this electric field, and that would be how much? That would be in this direction, and this force is simply Q. But if I put a negative charge, if I put a negative charge, then what would be the force? Then force would be in this direction, right? Force would be in opposite direction of electric field, and that would be minus Q. So that is the force on charge particle in external. Right? This is a very simple idea, and we will be doing some questions using these ideas. Right? So let's do some questions. So it's so a spherical conductor of radius 10 centimeter has a charge this distributed uniformly. What is the magnitude of electric field at a point 10 centimeter from the center of this field, right? So this is a spherical conductor, right? This part we have not studied, but I will just write that. This is the electric field of a sphere, right? Or this is a conducting sphere, right? So electric field of a conducting sphere. So for a conducting sphere, the electric field will have two parts. One would be inside, right? And the other is outside. Because we have a sphere, right? And this is a conducting sphere. So one would be inside this sphere, and the other is outside the sphere. So we want to calculate the electric field at these two points. So inside the sphere, the electric field is zero for a conducting sphere because all the charges are residing at the surface of the sphere. If it is conducting, then all the charges are at the surface. So there are no charges inside the sphere. So electric field inside the sphere is zero. Electric field outside the sphere is simply kq by r square. So that is the idea of conducting, right? Okay, now we can do this question. So what is the magnitude of electric field at a point 10, 15 centimeter from the center of this sphere, right? So we have the sphere, and this point is at 15 centimeter away from it. So let's say this is point P. So electric field at P point would be simply KQ by R square, right? So K is 9 into 10 to the power 9. Charge is 3.2 into 10 to the power minus 7 coulomb. And this is 1.5 centimeters. So this is 10 to the power minus 2. And then 1.5 centimeter 10 to the power minus 2. So how much is this? So 9 into 3.2 divided by 15 into 15, 225. This is 2.25. And then this is 10 to the power 9 minus 7. So that is 10 to the power 2 and then plus 2. So 10 to the power 6. So how much is this? So this is right. Let's think. So that would be nearly 10 to the power 7, right? Okay, so let's say that, yeah, so let's say this is 9 is nearly 10 to the power 10. So we can write, or we can multiply this. Right? So let's multiply this and divide and then let's see. So 9 into 3.2 equals divided by 2.5. So 12.8 into 10 to the power 6. So this is 1.28 to 10 to the power 7. And that is 10%. This would be the answer, right? Is it clear? So this is a direct question. So from electric charges and fields, if we remember the correct formula, then we can solve these questions. Yes, easy. Yes, yes, easy. Yes. This one is easy, right? Okay, yeah, quickly note this thing down and then we'll see the rest of the question. Friends, I have to, because the rest of the people are not here. Just quickly note this thing down and then we'll do the next question. Yes, whenever you have noted, just so now let's do the other question. The other question. Okay, so this one based on, so this one is based on the idea of force on charged particle due to the external. That we'll do in the next part for the next question. Right? These questions are 60, yeah, 63rd one will be that. Alright. So a particle of mass m and charge q is placed at rest in a uniform electric field and then released. The kinetic energy obtained by the particle after moving a distance y, right? So we have to find out the kinetic energy, and whenever we see kinetic energy and the velocity is given, then we know that from electric field we can find out what is the force, right? So force, distance, and kinetic energy. We have these three components. Then from force and distance, we can calculate work done, and then we know the relation between kinetic energy and the work done. So this, using these ideas, this question will become very simple, right? So we have to use or we have to apply the work energy theory, right? And one more point that we have missed. So yeah, the other point that I have missed in here, that what is the torque? Right, so this is also important topic. So torque on a dipole, right, in external electric current. So this thing is also important. What is the torque? This torque is simply P cross B, which is simply P sine theta. So this thing we also have to right, because when we will work the relation or when we the second chapter, so this would be important for us. So from this torque, we'll calculate the work done, and then we'll see that what is the potential energy of the dipole in the right? What is the work done? So these things. Yeah, so this is the talk on dipole in external. So now let us do this question. So we have to apply the work energy theorem, right? And what does this work energy theorem says that the work done is simply change in kinetic energy, right? Which is change in kinetic. Work done be K final minus K initial, because this thing was at rest, right? So K initial would be 0, and rest or starting from rest, starting from rest. So K initial is 0. Then simply work done would be simply K final, right? And what is K final? That would be simply half M. And what is the work done? So work done would be force into the displacement. So how much is the force? That is QP. And distance is how much distance? 1. And this is half M square. Also, what we need to find out? The kinetic energy. So we have to find out the kinetic energy, right? We don't have to calculate the velocity. Only want to find out the kinetic. Kinetic energy is simply like this would be the kinetic. Is it clear? Okay, good. So if it is clear, then put it down. And then we'll put questions and then yeah, we can questions. Questions. Yes, the class is deleted. Yes, that class is very kind of, Now it's equations. That equations. So infinite charges of magnitude q, each are lying at x equals to 1 to 3 meter on x-axis. The value of intensity of electric field at point x equals to, right? So intensity of electric field. So all these are whatever we were calculating. So that is the intensity of right? So we have to find out what is the intensity of okay, and we know that they will follow the superposition methods, right? So we have this x-axis. Let's say this is the x-axis, and let's say this is the y-axis. It would require the y-axis. At origin, so infinite charges of magnitude each are lying at each point. The value of intensity of electric field at point x equals to 0. At this point is x equal to 0. One charge is placed at this point, right? The distance is let's say distance q, and then another charge is placed at meters, right? This is one, and then another one is at 2 meters, and then the other one is at 4 meters, right? And then another one is at 8 meters, and so on. So these are the charges which are put at all these points. And then we have to find out, okay, so, and then we have to find out what is the electric field at p equal to 0 or at origin, right? So we have to find out electric field at, so all these are positive charges. So all these charges, the electric field would be in this direction, right? The direction is same for all these charges. So E naught, that would be simply E1 plus E2 plus E3 plus so on up to the end, right? And E1 is how much? That is K Q by 1 square. And then what is E2? That is K Q by 2 square. And then what is Q 3? So that is K Q by 4 square. And then so on, right? So how much is this? This KQ we can take the comma, and then this is 1 plus 1 by plus 1 by 16, and then 1 by 64, and so on up to infinity, right? So what is this progression called? What is this progression called? For here, so I thought that what. So what is this progression called? Is so whenever we have these kind of progression, so if we find out it by a, I am lagging for you. What is happening? Oh, okay. So if I calculate the ratio, then this would be 1 by 4 divided by 1. So that is 1 by 4. if I calculate A3 by A2, so that would be 1 by 16 by 1 by 4. So again, this is 1 by. So these are ratio and they are equal, right? These are R1 and R2. These are called common ratio. And if common ratios are equal, then it is called geometric progression. This is called G, right? And for this one, because common ratio is less than 1, so S infinity, you have to remember that S infinity is simply 1 over or A by 1 minus R. That is where A is the first term, and then this R is your common ratio. So if we apply this idea, then this would be simply K cube, and A is 1 divided by 1 minus 1 by 4. How much is this thing? So this is K cube, and this is 4 minus 1, so 3 by 4, so this is 4 by 3, right? Then what is this? Okay, then K is 9 into 10 to the power 9 cube and 4 by 3. So this is 3. So this is 12 into 10 to the power 9. That would be the electric field. So this is the correct option. Okay, is it clear for you? So we have to use the idea of the geometric approach. Right? We just